Every time I had to provide an information, it was because I was able to work with data and provide the information.
So there are 4 types of NoSQL databases. Examples of these applications for which IT professionals need to seriously consider graph databases include graph data structures are good for representing real-world entities and their relationships with few compromises, complexities, or contortions.
Hi, everybody. Welcome to the November edition of the Untapped Energy Meetup. My name is Mark Boulay. I am a data scientist with Synovus Energy, along with Tim Chan. I'd like to welcome you to the event tonight, which will feature a quick primer on graph databases with Yogi Schulz. Tonight will be Korang Modaressi, who will be speaking about data. He's been working in industrial projects for most of his career, professional engineer with a master's in mechanical engineering. And he's worked at Concave Research Lab analyzing model simulation data and studying transient fluid slosh behavior. I love that. He's published 6 papers as lead author and co-author, and he believes in the power of data efficacy.
And when I was asked to actually share some of the experience related to data and the information that could change things in a better way and actually add value. And I could share a couple of instances that I actually was engaged and involved to start with. I mean, back in the day, as a young field engineer in the construction site, I was there in a project that actually was installing and erecting the underground piping for a refinery. I was asked to actually maintain and manage the piping information there, and I was able to develop and implement a system, a database, to be able to track, trace the material and the status of those pools that was made and being installed. And by creating that system, actually, contractors are very careful about the material that they have to deal with, because sometimes they are free issued and client supplied. So one day I was in my office and my manager came to my office and proudly showed me the report that I gave him before he went to a meeting. And he told me that, Korang, I went with this report and I was able to tell them all the problems and provide them with the information that actually helped us to be a successful contractor, which it made me feel good, and I could see that I could be able to add value there. So that was a very good experience. Years passed by working as a project controls specialist in different projects. I used to work with different project teams using data and creating data and information for the projects. But years go by, and then I had to change a little bit of a gear shift I had basically in my learning experience, and I just started enrolled into a master's program. And there I was brought into this research program that was doing this fluid slush dynamics and the behavior of fluid slush inside a moving tank. I was part of the research team there. But again, working with data, I was able to, based on the simulation data, I was able to show the pattern between 2 dynamic behaviors in terms of the forces and the moments that was being introduced to the system, which led to a optimization or update of a formulation that a research team prepared years back to formulate the behavior, dynamic behavior of the slush. And it was one of those good experiences, because when I brought that observation, which was a correlation between these two factors, I didn't know at that time that I was just doing the correlation and data analysis, or sort of, but based on the pattern, the similarity of the behaviors, I brought to my advisors, and they were convinced that they had to go back to the formulation, and actually led to a way more simplified version of the formula that could be used in that kind of the analysis. And from that point, I could see that the table turned for me in terms of the credibility that I received from my advisors, and also from the research team in the lab. And it opened the doors for me to do more things that I was interested to do. So being an engineer, working in different projects, that's also enjoyable. But what I could see, every time I had to provide an information to make a difference, it was because I was able to work with data and provide the information. So this is expertise and knowledge that has been valuable all time, and it will be as we move forward, knowing that the data science is being developed and improved every day. So I think I enjoyed working with data, and I intend to keep doing so.
So now on to our keynote presentation, which is a quick primer on graph databases by Yogi Schulz. He's a long-standing member with Untapped Energy, presented for us a few times in the past, and we just love having him around for his wide breadth of knowledge with both the oil and gas industry and also the IT aspect of all this, which I'm learning more and more about every year. So Yogi founded Corvell Consulting, which over 35 years has specialized in project management and IT-related management consulting in the upstream oil and gas industry. He holds a BCom from the University of Calgary and is a member of PMI and CIPS, and holds its ISP designation. There's a lot of acronyms there, Yogi. He writes for itworldcanada.com, some really great articles there. Check them out, along with Computing Canada and the Calgary Herald, and has served on the board of the PPDM Association.
So graph databases have moved from a topic of academic study into the mainstream of information technology in the past few years. They're designed to treat relationships between data entities as equally important as the data itself. So that's a key differentiator from other database types, such as relational. So in a relational database, just to review, you have to perform a join before you can understand any relationships. Graph databases hold data without constricting it to a predefined model in the way that relational databases insist on. So those are two important differences to keep in mind with these graph databases. Okay, before we start, quickly to describe the Zoom controls. You can stay muted, please, and you're welcome to start the video if you want to show off your wonderful room that you're sitting in, and perhaps not your laundry room. You can look at the list of participants if you want by clicking here, and it'll open up this window. You can close up. You won't be sharing the screen. I'll be doing that today. And this is the important part, as Mark announced. Please do enter some questions in the chat, and Tim will moderate that at the end of my presentation. And if you want to give a reaction, a clap, or a thumbs up, you're welcome to introduce that at your leisure during the presentation. Okay, so who am I? I'm a founder of Corvell Consulting. I speak at a lot of different events, as Mark has already handled. We don't need to go into that any further. So here's what I want to talk about today. We'll start with some context about trends in information technology. We'll spend a bunch of time on the advantages of graph databases, and that's to explain why they're being adopted more and more, and where they might fit into the work that you're involved in. And then we'll spend some time on the disadvantages. If nothing is a silver bullet, as I hope we all know. So the disadvantages are about the immaturity of the technology that become risk factors for you and for the application that you're working on. We'll spend some time then on the different graph database vendors, so you'll have a sense of what they're all about, and we'll wrap up with some conclusions and recommendations. Overall goal of the presentation is to enhance our understanding of graph databases, and I'm hoping I can point you to some superior resources that you can explore in the future that will help you build your understanding further. And I hope that will help you prepare to tackle a graph database proof of concept at your organization. So starting with the presentation context, 3 major technology trends that indicate the adoption of graph databases will increase significantly or perhaps even dramatically into the future, because graph databases address the problems and opportunities created by these trends. The first is further DBMS developments. These we can leverage to address business problems and create business value. Then there's the digital data volume explosion. I think we've all heard about that. And in the context of today's presentation, it's what's taxing the limits of what relational database technology can deliver to us. And then we'll talk about some emerging applications. The trends that are creating the digital data volume explosion, such as IoT, social media, e-commerce, are also driving the emergence of new applications that benefit from the existence of graph databases. So we'll start with those 3 points. So just a little bit of history. To improve data management and data processing as data volumes grew, data management systems emerged as a separate software layer between the operating system and the application programs in the 1960s. Previously, all data was stored in the file system associated with the operating system of the machine you were using. So the first type of database that came along were called hierarchical databases. They have this simple tree structure that you see on the left of this slide. The dominant DBMS, and perhaps the only commercial one, was the IBM Information Management System, IMS. So has anyone here used IMS? Please click on reaction and then thumbs up. I'm not expecting many responses. All of you are just too young to have experienced this. Then came the network databases. They were the second generation and offered a richer structure starting in the 1970s, and the dominant DBMSs were Database, IDMS, and Total. And then along came the relational databases in the 1980s. And as you know, they've become and have remained the principal DBMSs. So however, the thinking about DBMSs didn't really stop. So let's continue on the next slide, and you'll see where it's taken there. In the 2000s, saw the emergence of XML databases and NoSQL databases. The idea that a database didn't need to be tightly structured in a purely tabular form. So there are 4 types of NoSQL databases that I want to make sure we're aware of. The first one is a document store. They store a key beside a complex data structure, which is called a document. However, don't think it's a Word document. Documents in this context are key array pairs or key value pairs. So example applications include catalogs, user profiles, content management systems. And there are a number of pieces of software. MongoDB, Apache CouchDB, and RavenDB are the major products in this space. Then we have the key value store. They store all data as key value pairs. They're the simplest database of all of these NoSQL databases, and they offer fast query and write operations. Example applications include user session details, preferences, real-time recommendations, advertising placement. And the examples of products in this space are Redis, Memcache, Apache Ignite. And then come the wide column stores. These types of databases store columns of data together instead of rows of data. And they're optimized for queries of very large data sets. And applications include IoT, geographic information, time series data. Example products are Cassandra and HBase. And then come the graph store, where we're going to spend most of our time today. And there are two flavors of this: the labeled property database and the resource description framework. And again, their advantage is the fast query, and they store these relationships explicitly alongside the data. Good applications of these are AI, fraud detection, roadmap, social connections. Example products are Neo4j, Allegro Graph, Tiger Graph. So just a reminder that these graph databases are not a substitute or an alternative for relational databases. The two types of databases will fulfill different data processing and different application objectives. So we're going to focus on the ones on the far right, the graph databases, and applications where they can be a superior solution. So we're all aware of the digital data volume explosion, I think. And part of our role in our organization, I hope, or I think, I expect, is to cope with this. So what are the sources of this digital data explosion? IoT is the explosion of industrial and consumer devices that monitor the performance of almost everything. There's also a flavor called IIoT, which we see a lot of in oil and gas. And these devices are replacing analog data recording devices. Then we have the digitalization of society. The most obvious example of this is the vast volume of digital data available to all of us on the web and its consumption by billions of people. Social media and e-commerce are creating huge volumes of digital data. The third one is graphic and video data types. Originally, digital data meant letters and numbers only. Now, we've added graphics and videos, and they've added many orders of magnitude more to the digital data that's available. And the last one is digital transformation of businesses and government. Many organizations are actively working to enhance application functionality, fill gaps in their application portfolios, and eliminate the remaining bits of paper and the mountains of Excel workbooks that exist between their applications. All these initiatives add significant digital data volumes. And then we have the voracious demand for data analytics. The data demands of data analytics triggered by the move to more data-driven organizations have also produced more volume. They don't just read it all. So all of this, these trends, which I think we've all observed, create a problem in many organizations. So perhaps this overloaded truck describes how our relational databases are struggling to cope with the application data they're supposed to manage. So the problem we have today is that the many DBMS advances, plus huge improvements in computing infrastructure performance that have been introduced over many years, are nonetheless straining or failing to handle these vast data volumes. So the solution to all this is applications that access graph databases can solve various data and application problems that are creating frustrations in the enterprise. So examples of these applications for which IT professionals need to seriously consider graph databases include the following: artificial intelligence, computing infrastructure modeling, monitoring, customer 360 interaction analysis, the digital experience that our customers are encountering, enterprise search, fraud detection, knowledge base, metadata management, master data management, natural language processing, product recommendations, social media influencer analysis, supply chain. So what's obviously missing are the many applications that relational databases handle very well. The transaction processing, or in fact short transaction processing that we see all day long in our existing data centers. Most of these applications require a much longer transaction to perform their work. So these applications all process large volumes of data. They all require the querying of multi-node relationships. And these applications all benefit from graph databases because graph databases deliver excellent performance for complex data analytics. They simplify data ingestion and integration from diverse data sources, and they manage vast volumes of data reliably. So that's the difference between these emerging applications and the ones that we're probably more familiar with that orbit in the relational world. Henry, it's for you. Apparently your heart is about to fail. Now, we all want to predict the future. And these relevant applications include production planning, logistics planning, financial planning, capacity planning. And when you think about the requirements of these applications, they include diverse data groups, huge data volumes, predictive data analytics, modeling capability, and fast response time. So I'm not sure we're going to get to the point where Amazon delivers a replacement heart, but it does tell us what we're after all the time. We want to be able to predict the future reliably, and graph databases play a role in that goal. Okay, let's move on to the advantages of graph databases. They're superior for handling highly interconnected data and for quickly producing concise results from complex queries. Relational databases, on the other hand, are more general purpose and do well with processing large numbers of short transactions. So for each of these advantages, I'll compare the graph databases to the relational databases. Query speed is what we'll discuss first. After all, we all want instantaneous results. Representations of relationships and data structures. Now, sometimes this is a topic that people yawn at and say, oh, that can't be important. Well, it turns out it is hugely important. These two advantages may surprise many because we've grown up to thinking that relational data models do a great or at least sufficient job. It turns out that relational data models constrain our representations of the real world. So graph databases give us a lot more flexibility there. Okay, let's just spend a moment on terminology here. A graph data model like this simple representation consists of nodes that contain the attribute data and edges that represent the explicitly stored relationships. And obviously nodes connect the, edges connect the nodes. So a relational model consists of entities, whoops, went a little fast there, entities and relationships. Now the potential relationships are expressed as foreign keys or joins. Now, some of you may be aware that there's more to graph data models and relational data models than these few concepts. You're right, of course, but these terms are enough to get us through our overview presentation here today. We're not trying to cram a data modeling course into the presentation today. Okay, so what about query performance? I said that was a big deal. So all end users are always impatient and expect quick response time. Nobody cares about how much query complexity consumes resources or how the vastness of the data volumes that must be traversed require elapsed time. Everybody's interested in producing a result. And DBMSs all work hard to respond to this expectations, and sometimes the expectation is just ridiculous. But let's look at this graph. It shows that the performance of graph and relational databases is about the same until the depth of relationships that must be queried exceeds 9. At that point, the performance of relational databases loses steam rapidly while the graph database continues to perform well. For graph databases, the query speed is only dependent on the number of concrete relationships that must be read and not the total data volume in the database. This focus on reading only the data directly related or closely related to the relationships being queried is what produces the super fast results. For relational databases, the query speed tends to be dependent on the number of tables that must be joined and the amount of data in every table being queried. This focus on tables and data volume means queries slow down materially as the number of tables and the data volume involved increases. So obviously you'll know that good index design, superior query optimization can reduce these speed losses, but often it's not enough. Now on this next table, we see something a little different in that the differences between the two technologies moves up gradually, there isn't this corner like you saw in the last graph. And eventually you can get to the point that the relational query in fact doesn't finish at all. So from a performance point of view, in some applications, graph databases have a huge advantage. Now,
sorry, Yogi, we just have a question from the chat. Stephen is asking, is that because many systems only have 8 cores?
Only have 8 what, relationships?
8 cores, like the computing power of the system.
Okay, we're talking about scaling. Okay, so we're going to talk a little bit about vertical and horizontal scaling. So obviously, if you put more CPUs, meaning more servers or more cores per server, you can perform more. But it turns out that the incremental benefit that each subsequent core gives you is less than the last one. So eventually you run out of steam. You can't just power your way through this problem.
I believe Stephen was asking about something on the previous slide, but it looks like you did answer his question.
Okay. Okay, so I see. You're asking if this 8 is related to the number of CPU cores.
Yes.
And the answer is no. The number along the x-axis is the depth of the relationships that you have to traverse in order to complete the query. So if you have, maybe the simplest way to say it is you have 8 joins in your select statement, you're good. Doesn't matter what technology you're using. But if you have 10 joins in your query, then all of a sudden the graph database has a huge advantage over the relational database, and the relational database slows down. So the short answer is no, that's not the number of cores. It's the depth of the relationships on the x-axis. I guess I could have explained that a little better. Thank you for jumping in with that question, whoever asked it, and thank you, Mark. So that was very helpful. Okay, let's turn to the representation of relationships. Whenever a DBMS can represent a real-world relationship accurately and avoid kludges or workarounds such as cross-reference tables or composite keys, it's easier for software developers to understand the organization of the data in the database. This ease of understanding leads to more accurate and reliable solutions with less software development effort. And of course, subsequently you get less effort whenever you have to put in an enhancement, which is almost forever. So, as I said earlier, for graph databases, the relationships are physically stored as data alongside the attribute data. And that contributes to the high performance. So this graph data model is a simple subset of a social network of music lovers. And the graph, this other graph data model is from the oil and gas industry. It's more complex. It represents the real world of oil and gas production ownership that's used in joint interest billing. So that's how you represent data in a graph database. In a relational database, as you know, that the relationships are defined through the value of foreign keys or through software logic. Now, foreign keys are incredibly useful to the point where they trigger too many joins, or worse, force a self-join. At that point, foreign keys cause a significant deterioration in query performance. Defining relationships through software logic makes it difficult to understand the relationships just looking at the database schema, and creates significant software maintenance efforts. So we try hard to stay away from that. Graph databases can more easily represent and query hierarchies of data as well, and they're more difficult for relational databases to cope with. Okay, now what about the representation of data structures? That's the other point I mentioned. So again, if we can represent the real world data structures as accurately possible, and with the minimum number of compromises, more of the benefits I just described can be realized. In this graph data model example, the number of boxes is exactly equal to the number of boxes in the real world model. Now, that may be a crude way to look at it, but it's a good sign of the ability of the graph data model to accurately represent the real world. So the data is still contained in tables, just like in the relational DBS, but the advantage is the table definitions or relationships can be altered dynamically. These characteristics are particularly important when the data doesn't have a specific format. A good example of that is a Facebook comments or posts that can consist of any combination of text, images, videos, links, and geographic coordinates. Now let's look at what the relational data model looks like for this same example. You'll notice, just very simply, there are more boxes in the representation. So again, why is that? Because we have the relationships being stored in extra tables and the use of foreign keys, and the data structures must be defined in advance. Changing the data structures in a relational database always requires careful impact analysis and planning, and introduces some risk in the transition. So, quick example, real world examples are probably a lot more complicated than this one. So here's another example of the same thing. Here's a relational data structure example. The mint boxes are the tables of the major entities. The white boxes are the tables required to describe the relationships. Now here we see exactly the same four mint boxes, and the white boxes here aren't tables, they aren't foreign keys, they're just the relationships that you saw on the previous slide, and that makes it easier to work with all of this. Okay, so the point of this Flintstones cartoon is to remind us that graph data structures are good for representing real-world entities and their relationships with few compromises, complexities, or contortions. Okay, let's move on to the disadvantages of graph databases. I'm discussing this topic because every technology has its pluses and minuses. We're going to talk about rapidly evolving technology that requires the customer to be aware of patches and new releases and plan a response. Difficult to scale. Some graph data products will only scale up to a certain point, notwithstanding its potential advantages. There's no standard language in the graph world yet, although one is emerging, as we'll discuss. There's a lack of parallelism in some of the products. That may or may not be a problem for you, depending on the application that you're looking at. And there are missing operational features that we're used to in the relational world. So these disadvantages should make you cautious about committing to deliver highly available, robust production quality applications on top of a graph database. Keep in mind that there are many valuable applications that exist that don't require these features. For example, most data science applications, data analytics applications, don't require real-time response. And if they crash or a task doesn't complete normally, they can be restarted without a lot of impact on anyone. So further, all the graph database vendors are attacking these and other issues with large development teams fueled by truckloads of venture capital. I suspect venture capitalists all have the recent Snowflake IPO in mind. I don't know if you caught that in September. Snowflake, in its IPO, opened at $120 and then climbed to above $300 and finally finished the day at around $240 a share. I wonder how many of the graph database vendors have that same exit plan in mind. We'll see how the next few years evolve. So, as more money is being thrown at these problems, these disadvantages will become smaller or disappear in the coming months and years. Okay, so the first one, rapidly evolving technology. Every graph data vendor is introducing major enhancements regularly while trying to work at the speed of this roadrunner. This is a good news, bad news story of great functionality enhancements amid almost constant change. This high level of product development creates difficulty comparing products if you're trying to select something, because the landscape is changing so quickly. It also can sometimes create product stability issue because it's so difficult to thoroughly test all this new software. So what are some of the examples that are coming down the road? High-speed data ingestion. Large data sets require high-speed ingestion, otherwise database loads can literally take days. Integrated data visualization. Why access the database with yet another software package, or worse yet, export summary data to visualize it? Native JSON and XML data formats. They avoid a lot of translation on import and output. NoSQL data structures. Most of the existing products just support one of the 4 data structures that I described earlier. We'll see more products that support more than one of those. We're also going to see specialized hardware, chips that perform much faster than the general purpose CPU chips. And we'll see a lot of application performance improvement from those chips. And we'll talk about them a little more later in the presentation. Support for both labeled property graphs that are simpler and semantic graphs that are more complex and more powerful. Integrated machine learning algorithms, offering algorithms rate as part of the database rather than forcing customers to develop their own. That adds a lot of values for customers and by reducing development effort. Document and entity enrichment, that means parsing unstructured data for entity values and to store that as a structured data. So many of these enhancements are about functionality, speed, flexibility, and these goals, of course, conflict regularly, and that's the challenge these vendors have placed them before themselves. And of course, the vendors are introducing this technology in response to competitive pressure and customer requests, 2 very good reasons. Okay, difficult to scale. I just want to show that most graph databases were initially designed for a 1-tier architecture, meaning a single server architecture. Some vendors have begun to offer what's called sharding, which is the functionality to distribute a database across multiple disk arrays. So there are 2 kinds of sharding. Vertical sharding is where you separate table columns into multiple different tables known as partitions. Each partition has a different schema and different columns. The data held in each vertical partition is unique and independent. And then the other way to do this is horizontal partitions. Each partition has the same schema and columns, but entirely different rows. And the data held in each partition is unique and independent. Now, the main appeal of sharding is that a database is that it can facilitate scaling as resource consumption grows beyond what one server, no matter how many cores it has, plus a related storage can handle. Some vendors have begun to offer horizontal scaling, which is the functionality to distribute the database across multiple servers. So we're adding more machines to an existing cluster to spread out the load and allow more traffic and faster processing. So just for completeness of discussion, there's also vertical scaling, which I touched on in response to that question, which involves simply upgrading hardware of an existing server by adding more RAM and CPUs. That doesn't require any database enhancements, but obviously has a limit. Now, you're probably aware that relational databases have supported sharding for many years, and it's new to the world of graph databases. Now, the no standard language. We're all aware that relational databases support the standard SQL language for queries, updates, and management of the relational database. I'm sure many of you have seen a diagram like this one many times. Although many vendors have extended this SQL language, every vendor supports the core SQL language. The standardization makes it easy to find and onboard experienced staff quickly and cheaply. Now, in the world of graph databases, every graph vendor has defined a unique syntax or a language for queries, updates, and management. So we have the Cypher query language is supported by Neo4j, who is a dominant graph database vendor. Gremlin is a component of the Apache Tinkerpop project, and it's supported by most graph database vendors. Gremlin and Sparkle have different uses. Gremlin is more for property graph databases, and Gremlin is a graph traversal language. And then Sparkle is mostly for what are called RDF, or Resource Description Framework triplets. So I've thrown a lot of acronyms at you, and I hope that you don't have to remember all of these. The key point is that most vendors support some version of Cypher, Gremlin, or SparkQL. Now, every vendor, of course, claims that their version is superior, but this lack of standardization creates a lot of hassles. Fortunately, most of the vendors are participating in ISO and W3C standards development efforts. And there's some hope that they're moving towards adopting a standardized language called GraphQL. So today, the picture is still a little murky, but in the next few years, I expect we'll see some progress on this problem area. Now, this lack of parallelism is another problem. It's the ability of the database engine to concurrently process multiple queries and updates submitted by multiple active tasks. Most end users of relational databases take parallelism for granted. Some graph databases offer parallelism and others don't. If it's important to you, this one feature may make your graph database selection decision for you, whether you wanted to or not. Missing operational features. Most database administrators of relational databases will take all these operational features for granted. They exist either in part, in the relational world, they are either part of the DBMS or in another supporting software package that the client has licensed. In the world of graph databases, many of these features either don't exist, they're rudimentary, or they're under development. So I don't know if we need to go through every one of these. I don't know how many of you are DBAs, but DBAs care about these a lot. Okay, so crafting an appealing NoSQL resume. Do you have any experience in SQL? No? Doesn't matter. Just write down expert in NoSQL. So the growth and adoption of all types of NoSQL databases, including graph databases, represents a career development opportunity for IT professionals of all kinds as this technology is adopted more and more. Okay, so who are the graph database vendors? Let's look briefly at these, and we're going to talk about the top 10 databases, popularity, and the top 10 graph databases. Okay, so some of you may have been at this website called DB Engines. I've cut out the top 10 databases by popularity. No surprise, Oracle, MySQL, Microsoft SQL Server are right there at the top of the list. The top document database here is number 5, and IBM DB2 is number 6. So not surprisingly, the relational databases occur at the top of the list. They've been around for decades longer and have huge install bases. Now you may be wondering, well, how is this ranking determined? Essentially, this is by frequency of mention ranking, or it's a buzz ranking. It's not about revenue or market share or something like that. So different products will show up in a different order. And if you go to this website, you can get the whole list, which goes on for 100 different products. Okay, focusing on the graph databases, Neo4j is typically at the top. Microsoft Azure Cosmos, Arango, Orient, Virtuos, and then Amazon Neptune. So the Microsoft and Amazon graph databases are cloud offerings from these cloud service vendors that appeal to many organizations. So, but that doesn't matter. You can host the other graph databases in the cloud or on premise. It's really your choice. In the DB Engine's definition of graph databases, it does not include document. So they're in their own category. So let me show you that. Here are the document databases, Mongo, Amazon, Azure. So Amazon and Microsoft both have an offering in both these camps as well. So there are a lot of products available, and I invite you to do some serious research before you commit to one of them. Looking at it over time, how do these as a popularity trends. Neo4j has been a consistent leader. Notice how Microsoft Azure has come up from the middle of the pack to the #2 spot. And Amazon Neptune is a newer product with less track record and less following at the moment. But I would never bet against either Microsoft or Amazon when it comes to gaining market share and credibility in the market. Here's a set of about 100,000 data sources full of bits of well data. Please consolidate and integrate them into one meaningful data warehouse. I don't know if you've ever been in a meeting where that was asked for. Often managers have no idea how difficult data integration is. In every case, data integration work is preceded by major amounts of data cleanup. Be very careful to manage expectations about how much effort and elapsed time this work will take. Project managers are often bludgeoned into committing to budgets and schedules before anyone has a credible idea of the issues the project will face to achieve the stated goal. In this situation, selling a proof of concept is an excellent way to explore the likely issues while not committing to any deliverables that anyone expects to move to production. Start projects with the smallest, cleanest data sources where you anticipate you can deliver the most business value and have the most interested end users signed up to participate on the project. With that small success under your belt, you'll typically have built some credibility to tackle the next and slightly more ambitious project. It's amazing how we work with dirty data in many organizations. Okay, so wrapping this up a little bit, what's happening in the future? We'll look at software and hardware developments that will improve graph databases, and then we'll wrap up with some conclusions and recommendations, and we'll discuss the questions that have piled up in the chat. Future software development. Here's what we'll see in the near term that will make these products more appealing and more widely adopted. First is response time. Graph databases will increase their response time lead over relational databases. Data ocean, this is my take on large data lakes. So graph databases will continue to increase their ability to cope with, manage, deliver value from skyrocketing data volumes. Flexibility. Graph database features will enable applications to become more responsive to rapidly changing business requirements with lower cost and risk of creating an unplanned application outage. Diverse data integrations, databases will further expand their ability to expand their rich library of tools to integrate data from diverse sources. This data integration software will become easier to use, point out illogical constructs, and alert end users about data quality issues and data integration disconnects, and they'll automate the high effort, mind-numbing data wrangling work that goes on now. Systems development velocity. Graph databases will come packaged with components to boost software development productivity and ensure acceptable software quality. Components include an increasingly capable integrated development environment and more productive data integration tools. Algorithm library, we talked about that briefly before. These will continue to expand and include in-database support for analytics, machine learning, handling data quality issues, and handling some kinds of software inadequacies. Graph query language, we've talked about standards before, so a capable query language that's consistent with emerging standards will emerge, and that will make it easier to compare the functionality of graph database products and make it easier to train and redeploy staff. Graph database operations, they'll become more sophisticated and less tedious and have the tools that I listed on that previous slide. And role-based security. Graph databases will include more features to support role-based security to reduce software development effort and also to reduce operational effort to manage these roles. Now, actually, there are some hardware developments that are interesting as well. The first one is called non-volatile memory Express. That's quite a mouthful. And this is actually a standard that solid-state drives are using to increase application performance and significantly reduce recovery elapsed time after a power failure or a system crash. User programmable solid-state drives, we tend to view SSDs as many little black boxes that offer fast storage performance. It's easy to forget that SSDs include a processor. Recently, some manufacturers have begun to provide an application interface to that processor that leads to SSDs being thought of more as software-defined storage, and that can further accelerate input-output performance. Then we have field programmable gate arrays. Adding these to a multi-CPU server cluster can dramatically increase capacity, throughput, and performance for graph database applications. FPGAs improve performance by offering massively parallel processing architecture, pipelining parallel computations, and offer a much higher memory to CPU bandwidth. And then we have graph processing units. I think you're probably familiar with those from the world of gaming. We use these chips here for matrix multiplication to really speed up creating training data for machine learning. And last on this list is the programmable network interface cards. As Ethernet speeds have increased and are continuing to increase, these NICs have actually emerged as a bottleneck in application performance. So to avoid taxing server CPUs with packet processing, the emergent solution is to add processing capacity to the NIC itself. If you're wondering how important these technologies really are, consider that AMD, the CPU chip maker, just paid $35 billion, B for billion, to acquire a company called Xilinx, Xilinx, the leading manufacturer of FPGAs, in October 2020. So these hardware developments will benefit the performance of all applications, not just graph database applications. And I'm sure we will voraciously consume all of this new capacity with fancier applications and fancier models. Okay, in conclusion, graph databases will grow in importance in the coming years due to their advantages. More organizations are implementing one or more of the applications I listed earlier. Adoption of graph databases is growing. That's the motivation for giving this presentation today, to provide everyone with a general understanding of this technology. Graph databases will coexist with relational databases for many, many years to come. No one should think that graph databases are going away. They've proven their worth for many decades and continue to do so to this very moment. And relational databases are implementing some of the technology advances that I've talked about into their products. So it's an arms race between these two databases and a few other types of databases. So the conclusion, I think, at the personal level, is that building skills in the use of graph databases will enhance everyone's career in the world of IT. So what are my recommendations? What am I inviting you to do? First of all, I'd suggest you review the resources at the end of the presentation. There are links to articles. There are links to TigerGraph videos and the presentations at the TigerGraph conference. And there's links to the Nodes 2020, that's the Neo4j conference that was held recently as well. I invite you to read Gartner's Magic Quadrant for Data Management Solutions. It has a lot of discussion of the various types of NoSQL databases, including graph databases. And consider conducting a proof of concept using a graph database. You can start by identifying a poorly performing application that exhibits these characteristics: complex SQL meaning multiple joins in one select statement, the use of recursion or self-joins to tables, and large and growing data volumes. And if you can't find one of those, talk to someone in the business and dream about solving a problem they've been unable to tackle due to complexity. And to conduct your proof of concept, these vendors all offer free licenses, and the cloud providers all provide a free virtual machine instance. So that's an easy, simple way to run a proof of concept to get you started with this technology. And the vendors, of course, hope that you'll get hooked on their particular flavor of the technology. So with that, we should open it up for questions. Do we have anyone who wants to ask a question? And before we get to that, I'm just going to scroll through these resources at the end of the presentation. So you're welcome to have a look at that.
Thanks, Yogi. That was fantastic. You gave a very exhaustive viewpoint on the usefulness and some of the downfalls of graph databases. I'm going to give you a slightly more down-to-earth DIY-er perspective on graph databases than some of the open source packages that I've used in the past. So this, if you feel like doing this yourself and yet you don't have access to some of the tools that Yogi was mentioning, I'll show you some of the things you might be able to do at home. And so this is a very loosely connected journey through graph databases that I've taken on a bunch of different levels. For instance, hopefully you can see my screen right now. It has a little graph here that I used actually to kind of map out some project goals for a specific project at my company. And just want to make sure.
Yeah, we can see your screen, Mark.
Perfect, thank you. Okay, and so for instance, we were just trying to identify what next steps we would go through with this specific project. And of course, it started becoming highly nonlinear, and some things were dependent on other things and that kind of thing. So I just thought, hey, what the heck, maybe I'll build a graph database out of this. And this is what you see here. So you can kind of move along. We had some specific data. I'm not going to get into details here in any way, shape, or form. It's just the idea of what this might look like. But we have some specific data. How does it feed into a specific result that we're looking for, and what can we leverage from that one result to another result, for instance? So it can go off in different directions, and that feeds from this piece out to here where we build a machine learning model, and that moves off to this piece, and that can move off to that piece. So it's kind of a neat little way of trying to visualize a specific methodology or a problem set that you're trying to determine. And this is very simply, all I did was put it into a spreadsheet, and pretty straightforward. I have my nodes, as Yogi had mentioned earlier, where I have node 1, node 2, node 3, node 4, the title, the results, some attributes that are attached to that. And then here I just have the edges. So I'm going to say, okay, well, I need to connect node 1 to node 2, and I have one-way arrow going to that. Node 1 to node 4, which I believe is shut-in times to geological data. If we go take a look at that, shut-in times to geological data, we can see that there's a two-way arrow here. So that means that this can help inform this, and then that can help inform that. So pretty straightforward process. So you can see the data itself can be very straightforward, depending on what your problem set is. So just to let you know, this was built in a package called Viz Network, which is an R package. We're using Shiny within our company to display this. So this is the package I kind of landed on. I used it because it has a ton of different customization options. And so I kind of got lost for a day or two in those, but it was a lot of fun. And Viz Network actually leverages off of a JavaScript library, like pretty much the entire world does online, called viz.js. And so that's a package that you can use. And there's also a Python version of that called PyViz. So you can use that as well. And so this is what an example might look like within Python, for instance. So lots of fun where you can kind of play around, and they have great physics models that you can kind of get very addicted to playing with, for instance. If you're a Python user, there's also, I think, probably one of the de facto packages for creating network or data network graphs called NetworkX. And so I've used that a little bit too, and that's what this could look like. This unholy mess basically came from a problem set that I had to work on through my current master's program, in which we had to define the similarity of these little 64 by 64 pixel images, trying to map them out and map what their similarity looks like. So I use NetworkX for that. And that's what this looks like. So each one of these dots actually has at least 100 edges to another node, to other nodes, sorry. And the idea here was just to identify what actually is classified as a similar image. And I thought initially it might be just the way that this face is pointing, whether it's pointing right, left, up, or down. And so there's a bit of difference in how those are looking, like all these fellows down here are looking to the left. These generally look to the right. But ultimately, it seems that it was actually the luminosity of the image that mattered. So you can see on the top right here that all of these are very dark. And then as you move away from there, they get lighter and lighter, and they just happen to coincidentally be pointing in the same direction often. But it's really the darkness there. So you can see this is one aspect of something you can do with a network graph. And finally, if you are a masochist and would love to use D3 to build a graph database, or sorry, a visualization, this is another example. And this one makes no sense because this was a homework assignment, so the labels and everything don't make a lot of sense. But in essence, it's just mapping different NBA teams and how they connect together. So here, I'll pin this little fellow here, and then you can see some of the different ways you can kind of connect things with. D3 is a very powerful visualization library, and so you can see how you can collect things with different lines, different thicknesses. The actual nodes themselves have different colors, that kind of thing. It was just meant as a customization exercise, but it's a fun little one to play with, and it has a very, very responsive physics engine. So just wanted to give you an idea of some of the things you can do at home and play with some of these graph databases. Just find something that's relational, right? Or sorry, that has relationships, sorry, not relational, but relationships. And then you can map some of these things out. It's a lot of fun to play with, and I really enjoyed using some of these different data sets and try to look at data in a slightly different way.